Some of the greatest minds in history predicted our universe's strangest behaviors, only to be completely forgotten. These 27 geniuses saw the future of physics, from black holes to dark energy, long before anyone else. Their revolutionary ideas were buried by time, bias, or simply being too far ahead of their era. By the end of this journey, you will know the hidden stories behind the cosmic truths we are only now confirming. Why were these prophets of science erased from our textbooks? And what other secrets might still be hiding in their lost work? How much of what we call modern discovery is actually a rediscovery of a much older, deeper wisdom? The legendary Library of Alexandria once held the accumulated knowledge of the ancient world, a universe of ideas contained within its scrolls. Its destruction serves as a haunting reminder of how easily entire worlds of genius can vanish into smoke and ash. This was not a singular tragedy but a pattern repeated throughout history, where revolutionary thinkers are systematically overlooked. Societal biases, a lack of powerful patrons, or ideas simply too advanced for the available technology have all conspired to bury brilliant minds. For centuries, the comfortable dominance of the Earth-centered universe model actively sidelined anyone who dared suggest the Sun was the true center. Their contrarian voices lost to the weight of established dogma. Historian James Burke aptly describes innovation not as a straight line of progress, but as a messy, tangled web of forgotten connections and suppressed ideas. This is the fertile ground from which our forgotten geniuses emerged, their manuscripts languishing in dusty archives while mainstream science slowly, painstakingly, caught up to their predictions decades or even centuries later. Political turmoil could isolate a scholar, while personal obscurity could prevent their work from ever reaching the right eyes. It makes you wonder, how many radical ideas being dismissed as fringe science today will be the established truths of tomorrow? Against this backdrop of historical oversight, the stories of these individual prophets of physics become even more poignant and powerful. Alone in his Colorado Springs laboratory, Nikola Tesla carefully documented rhythmic signals intercepted by his colossal magnifying transmitter. He was convinced these were not random atmospheric noises, but deliberate communications, perhaps from Mars. Long before modern search for extraterrestrial intelligence programs existed, Tesla was listening to the cosmos, believing the universe itself hummed with intelligent energy. His entire world, was built on a simple, profound mantra. If you want to find the secrets of the universe, he said, think in terms of energy, frequency, and vibration. This was not just a poetic phrase. It was the core of his life's work. He envisioned a cosmos woven together by an invisible fabric of resonance, where energy could be transmitted wirelessly through the ether, a concept that seemed like magic to his contemporaries. Today, that idea feels eerily familiar. We now map the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, a literal vibration from the birth of everything. We hunt for gravitational waves, ripples in space-time caused by cataclysmic cosmic events, which are essentially the universe ringing like a bell. Tesla was listening for the universe's song with equipment he built by hand, hearing a prologue to discoveries we are only now confirming. His revolutionary work on alternating current and wireless power was more than just engineering. It was a practical test of a unified field theory, a hint that all fundamental forces are interconnected through intricate vibrational patterns. This idea lies at the very heart of string theory, one of today's most ambitious physics frameworks, which proposes that the smallest building blocks of reality are tiny, vibrating strings. Tesla dreamed of tapping into the cosmos's own energy grid and opening conversations with other worlds. These visions, which led to his financial ruin and public ridicule, now directly inform our most advanced research into dark energy and interstellar communication. It is a haunting thought. What if his funding had never been cut? What if his Wardenclyffe Tower was completed? We might have unlocked the universe's vibrational secrets a full century ago. Tesla's story is a stark lesson in how a mind too far ahead of its time can be tragically misunderstood. His genius fading into obscurity while the world slowly catches up to the frequencies he once tried to teach us to hear. While Tesla listened for the universe's hum, another quiet mind was contemplating gravity's ultimate power. In the late 1700s, a country parson named John Michell sat under the night sky from his peaceful vicarage and envisioned what he called dark stars. Using only Isaac Newton's laws of motion and gravity, Michell performed a startling calculation. He reasoned that if a star were massive and dense enough, its gravitational pull would be so immense that not even light, the fastest thing known, could escape its grasp. He was describing a black hole. Over 2 centuries before the term existed or Albert Einstein's theory of general relativity provided the modern framework for understanding them. Michell's genius was in applying the simple, elegant physics of his day to its most radical conclusion. He even proposed a way to find these invisible monsters, suggesting we could detect them by observing the wobble of nearby visible stars tugged by their immense gravity. This is precisely the method astronomers use today to identify black hole candidates in binary star systems. It is a breathtaking leap of logic. A clergyman using classical tools to predict one of the universe's most bizarre and violent phenomena. His paper was published and then, for the most part, completely forgotten, buried by the scientific consensus of his era. The idea was simply too far ahead of its time. It wasn't until the 20th century, when physicists like Subramanian Chandrasekhar calculated the conditions for a dying star to collapse under its own weight, that Michell's dark star was resurrected from obscurity. The irony is profound. A man of the cloth, in a quiet moment of reflection, foresaw the cosmic abyss. His story forces a haunting question. How many other fundamental truths are sitting patiently in old journals, waiting for the world to become clever enough to understand them? While John Michell predicted the darkness of collapsed stars, Katherine Johnson illuminated the precise pathways between them. She sat at her desk, a human computer armed only with a pencil, a slide rule, and a formidable intellect, charting the course for humanity to touch the heavens. Her calculations for Alan Shepard's first American spaceflight and John Glenn's orbital mission are rightly legendary, ensuring these pioneers could venture into the unknown and return safely. But behind these life-or-death missions lay a deeper, quieter genius. Johnson was unraveling the complex dance of celestial mechanics itself, solving orbital problems so advanced that no electronic computer at the time could be fully trusted with the answers. She worked with equations describing orbital resonance, the subtle, repetitive gravitational tugs that can lock celestial bodies into stable, rhythmic patterns or fling them into chaotic trajectories. Today, we see these same resonances shaping entire solar systems, governing the unusual orbits of exoplanets around distant stars. Johnson's math was effectively mapping the invisible architecture of space, predicting how objects move under the competing pulls of multiple gravitational forces. She applied and refined mathematical techniques pioneered by Leonhard Euler, developing new algorithms by hand that accounted for tiny perturbations, the small gravitational nudges from other planets and the moon's lumpy shape. In doing so, she was modeling behaviors like orbital precession, the slow, steady rotation of an orbit itself, a phenomenon crucial for understanding everything from Mercury's path around the Sun to the stability of satellites. Her work for the Apollo program, plotting a safe course to the moon and back, directly engaged with the infamous three-body problem, the immense challenge of predicting the motion of 3 gravitationally bound objects. Her solutions were so elegant and accurate they helped bring astronauts home. Now, That same complex problem helps us explain the strange, looping orbits of planets in binary star systems and the clusters of Trojan asteroids that lead and trail planets in their orbits. Katherine Johnson's story is a powerful testament to how practical, immediate problem-solving can reveal the universe's most profound operating principles. Her genius worked within the constraints of mission deadlines and the silent, vast language of mathematics, incrementally building our understanding of cosmic motion. She looked at the sky and saw not just a destination, but a beautiful, calculable chaos. Her legacy reminds us that the maps to our greatest discoveries are often drawn in the quiet moments before the journey even begins. And just as she calculated the paths through our celestial neighborhood, another mind was contemplating the entire universe stretching and growing before our very eyes. Georges Lemaître sat with Einstein's own equations and saw a story they did not tell on their own. This Belgian priest and physicist proposed in 1927 that our entire cosmos, every galaxy and star, originated from a single point he called the primeval atom. He envisioned this cosmic egg exploding and expanding, fragmenting to form the universe we inhabit today. This was the Big Bang theory in all but name, years before the term was ever coined and decades before it became a cornerstone of modern science. Lemaître's genius was in taking the mathematics of general relativity and following them to their ultimate, startling conclusion. The equations pointed to a universe that was not static, but dynamically growing, and if you ran the clock backward, everything would have to converge to a single point of infinite density in a finite past. This was a radical departure from the popular steady-state model of an eternal, unchanging cosmos. When Edwin Hubble later observed the redshift of galaxies, showing they were all rushing away from us, it was a dramatic confirmation of Lemaître's expanding universe. Yet, his profound contribution was often overshadowed. Some of his scientific peers were skeptical, perhaps uneasy with the way his theory as a Catholic priest dovetailed with a notion of creation, even though Lemaître himself carefully separated his scientific work from his theological beliefs. He insisted his theory was neutral on the concept of a creator, dealing purely with physical processes. His prediction of a definite beginning for the universe was a monumental shift in thought. It directly anticipated the discovery of the cosmic microwave background, the cooled remnant of that initial explosive heat, and it laid the conceptual groundwork for our modern understanding of the inflationary epoch and the formation of the first elements. Lemaître's story is a powerful reminder that profound truths can emerge when we allow different ways of knowing to inform one another. He looked at the cold math and saw the birth of everything. But if the universe began with a single cataclysmic event, what about the bizarre rules that govern the tiny world within the atom? The same era that gave us a new cosmic beginning also spawned geniuses who predicted the strange, probabilistic heart of quantum reality. John von Neumann built the mathematical skeleton of quantum mechanics while secretly wondering if consciousness itself gave it life. This was not a minor hobby. As he rigorously defined quantum states within the abstract realms of Hilbert space, he privately speculated that the collapse of a wave function, the moment a probability becomes a definite reality, might require a conscious observer. It was a breathtakingly radical idea, suggesting that the universe remains a blur of possibilities until a mind looks at it. His formal work gave physicists the essential tools, the operator theory and mathematical language, to calculate the behavior of atoms and particles. Yet his more philosophical leanings, discussed with colleagues like Einstein, were often set aside as unscientific musings. Now, decades later, his intuition finds echoes in modern investigations. The theory of quantum decoherence explains how interactions with the environment can cause quantum systems to behave classically. But the deeper question of the measurement problem, of why one specific outcome manifests, remains. Some researchers in quantum cognition even explore whether our own thought processes leverage quantum effects. Von Neumann's mind did not stop at the edge of physics. He also conceived of self-replicating automata, machines that could build copies of themselves. This was not just a precursor to von Neumann probes in astrobiology. It conceptually mirrors how information can propagate like a virus through quantum fields, or even the foundational code of a simulated universe. His unique genius was an ability to see the profound physical implications hidden within the purest mathematics, allowing him to foresee the bizarre non-locality of quantum entanglement, where two linked particles instantly influence each other across any distance. One has to wonder what other predictions are waiting in his unpublished personal notes, ideas that were simply too far ahead for his time. This journey into the quantum foundations of reality naturally pulls our gaze toward the possibility of unseen worlds, of hidden dimensions first mapped by another forgotten visionary. Theodore Kaluza mailed a letter to Albert Einstein that contained a secret map of the cosmos, one with an extra fold in space itself. A relatively obscure mathematician, Kaluza proposed a breathtakingly elegant idea in 1919. He suggested that by extending Einstein's own equations of general relativity into a fifth dimension, the two great forces of gravity and electromagnetism could be seen as a single, unified phenomenon. In his framework, electromagnetism was not a separate force at all, but merely the manifestation of gravity operating along a spatial dimension so tiny and curled up that it was completely invisible to us. Imagine the universe as a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant, you would discover its two-dimensional surface. A whole new direction to move in that was hidden from the larger view. Kaluza was saying our entire reality might be like the surface of that hose, with at least one hidden, compactified dimension governing the fundamental forces we experience. Einstein himself was initially captivated, writing back that the idea had never occurred to him and that he found it formally very compelling. Kaluza's work, later refined by physicist Oskar Klein into the Kaluza-Klein theory, was a monumental prediction. It directly foreshadowed the core concept of string theory, which requires several extra, compactified dimensions to make its equations work. Yet, the theory languished for decades. Without any conceivable way to test for a hidden fifth dimension, and with Kaluza working in relative academic isolation, his brilliant unification was largely dismissed as a mathematical curiosity, a beautiful idea with no connection to physical reality. Today, that verdict has been overturned. Physicists running experiments at the Large Hadron Collider actively search for evidence of these extra dimensions, looking for particles or energy that seem to vanish into a hidden direction in space. Kaluza's story is a pure example of mathematical beauty, pointing toward a physical truth long before our machines could catch up. It forces a profound question. If one of our universe's most basic operating manuals is written in more than 3 spatial dimensions, what other fundamental aspects of reality are simply geometric illusions? This idea of hidden dimensions would soon evolve into an even more radical proposition, that our entire universe might be a holographic projection from a lower dimensional surface. David Bohm saw the universe as a cosmic magic trick, a breathtaking illusion unfolding from a hidden, deeper order. While working on the Manhattan Project, he grew deeply troubled by the prevailing Copenhagen interpretation of quantum mechanics, which stated that particles do not have definite properties until they are measured. To Bohm, this was not a complete picture. He proposed a radical alternative, the pilot wave theory, where particles are guided by a subtle, non-local quantum potential, an invisible field that connects everything instantaneously across space. This was years before physicist John Bell formulated his famous inequalities to test for such hidden connections. Bohm was essentially describing quantum entanglement as a fundamental feature of reality, not a bizarre exception. His concept evolved into the stunning idea of the implicate order. Think of reality as a rolled-up carpet. The beautiful, intricate pattern you see when it is unrolled is the explicate order, our familiar world of separate objects and events. But in its rolled-up state, the implicate order, every part of the pattern is enfolded into a unified whole. In this view, every particle, every galaxy, is a unique unfolding from this underlying, entangled totality. Bohm was mathematically describing a holographic universe decades before it became a mainstream theoretical pursuit. He suggested that the information for the entire cosmos could be encoded on its boundary, and our three-dimensional reality is a projection from that two-dimensional surface. His collaborations with the philosopher Jiddu Krishnamurti further convinced him that consciousness was not a mere spectator, but an active participant in this unfolding. He saw mind and matter as two expressions of the same deeper reality, a view that resonates with modern panpsychism and theories of integrated information. For this holistic vision, Bohm was largely ostracized. His challenge to the Copenhagen orthodoxy led to his blacklisting during the McCarthy era, and his work was dismissed as pseudoscience by many prominent physicists. Yet, his predictions are now being validated. The successful confirmation of Bell's theorem proved that non-locality is real, that the universe is fundamentally interconnected in the way Bohm insisted. The holographic principle is now a serious candidate in the quest for a theory of quantum gravity. What if his voice had not been silenced? We might have already grasped how consciousness fits into the cosmic equation, and perhaps even solved the mystery of how the large-scale universe emerges from the quantum realm. Bohm's legacy is a universe whispering its deepest secret, that separateness is the illusion and wholeness is the fundamental truth. This profound sense of an interconnected cosmos, where information is woven into the fabric of space, leads us directly to the next genius who discovered the universe's faint, fossilized whisper, the echo of its very first moment. Kristian Birkeland's laboratory glowed with miniature auroras, shimmering curtains of light dancing around a magnetized metal sphere. He called this device a Torella, a miniature Earth, and with it, he recreated one of our planet's most breathtaking spectacles right on his workbench. In the early 1900s, while others still speculated that the northern lights were reflections of polar ice, Birkeland correctly proposed that they were born from the sun. He theorized that our star constantly emits a stream of invisible, charged particles, and when this river of energy encounters Earth's magnetic field, it is funneled toward the poles, exciting the atmosphere into a brilliant, silent display. His Torella experiments beautifully demonstrated this cosmic connection. Inside a vacuum chamber, he would beam electrons toward the magnetized sphere, and along its magnetic poles, ethereal glows would appear, a perfect, luminous echo of the real aurora borealis. But Birkeland saw something even grander in these laboratory lights. He realized the same electromagnetic forces accelerating particles in his device were also sculpting the universe on a colossal scale. The immense jets of matter shooting from young stars or erupting from the cores of active galaxies, he suggested, were simply these same cosmic currents operating over astronomical distances. He envisioned space as a dynamic medium crisscrossed by vast electrical circuits, a radical departure from the view of a static, empty void. For this prescience, he was largely ignored. The technology to directly detect the solar wind, that stream of particles he predicted, would not exist for another 50 years. The scientific establishment, comfortable with a placid cosmos, dismissed his ideas as the fanciful speculations of a man playing with glowing orbs in a lab. Yet, his perseverance laid the foundation for the entire field of heliophysics. Today, we know the solar wind is real, and we study its interactions with planetary magnetospheres as Birkeland currents, a permanent tribute to his foresight. His work anticipated our understanding of solar flares and the immense magnetic fields that structure entire galaxies. He proved that the secrets of the cosmos can sometimes be found not only by looking up at the sky, but by building a small, glowing piece of it right here on Earth. His story is a testament to the power of a simple, elegant experiment to reveal truths that the universe itself is not yet ready to prove. Just as Birkeland revealed the invisible currents flowing from our sun, another mind was deciphering an even more profound motion: the discovery that the entire universe is not just expanding, but flying apart at an ever-increasing rate. Arthur Eddington saw numbers as the universe's deepest language. After his famous eclipse expedition confirmed Einstein's general relativity, his mind turned to an even grander puzzle: the fundamental constants of nature. Why is the speed of light exactly 299,792,458 meters per second? Why does the force of gravity have the specific strength it does? Eddington became convinced these numbers were not random. He spent his later years in a profound, solitary quest to derive all physical constants from pure reason and mathematical relationships, believing they were all inextricably linked. He proposed that the cosmological constant, that lambda term Einstein initially inserted and then discarded from his equations, was not a mistake but a crucial key. Eddington speculated it governed the energy density of empty space itself, a force that would drive the cosmos to expand. This was a direct foreshadowing of dark energy, the mysterious force we now know is causing the universe's expansion to accelerate, a discovery that would not be confirmed for another 70 years. He even calculated a specific number for the total count of protons in the observable universe, suggesting this vast figure was fundamentally connected to the strength of the other constants. In doing so, he was inadvertently brushing against the anthropic principle, the idea that the universe's constants appear fine-tuned for life because, in a vast multiverse of possibilities, we exist in one of the rare pockets where the numbers allow it. His work on stars further revealed this prescient intuition. By calculating how stars could burn for billions of years, he correctly deduced their energy came not from chemical combustion or gravitational contraction, but from the subatomic fusion of hydrogen into helium, predicting nuclear fusion as the stellar engine long before the process was formally understood. Yet, for this breathtaking holistic vision, the scientific community often dismissed him. His elegant numerical relationships were criticized as mere numerology, a philosopher's game rather than hard physics. But modern string theory and the ongoing search for a theory of everything are, in essence, the fulfillment of Eddington's dream, a quest to find a single, elegant framework from which all constants and forces naturally emerge. His story is a powerful lesson in how a deep, intuitive belief in cosmic harmony can guide science toward its most profound discoveries, even when the path seems unorthodox. He listened to the subtle music of the constants and tried to write down the score. And just as Eddington pondered the fixed numbers governing reality, another theorist was imagining a dimension where the most fundamental property of all, time itself, could become fluid and relative. John William Dunne, an aeronautical engineer who designed early military aircraft, found his mind soaring into a different kind of sky altogether, the architecture of time itself. While flying through the clouds, he began to have strangely vivid dreams that seemed to contain fragments of future events. Rather than dismissing them as coincidence, he applied an engineer's rigorous mind to the problem, developing a radical theory he called serial time. Dunne proposed that our consciousness is not trapped on a single timeline. Instead, he suggested we exist within multiple, nested dimensions of time, much like how we move through 3 dimensions of space. In this model, the past, present, and future all exist simultaneously in a block universe, a concept now known as eternalism in modern physics. Our waking mind, he argued, is usually focused on just one strand of this vast tapestry, but in the relaxed state of dreaming, it can drift across the layers, catching glimpses of what we call the future. He detailed this in his 1927 book, An Experiment with Time, where he encouraged readers to keep dream journals by their beds to test his hypothesis for themselves. His mathematical framework treated each moment not as a fleeting point, but as a fixed location within a higher dimensional manifold. This is startlingly similar to how physicists today treat events in spacetime, and it resonates with emerging ideas in quantum mechanics, like time-symmetric theories where effects can sometimes precede their causes. For a while, his ideas captured the public imagination, but the scientific establishment quickly dismissed him. His work was labeled pseudoscience, a fantastical mixing of metaphysics and psychology that had no place in serious physics. Yet, Dunne's serial time anticipates our most current puzzles. Why does time have an arrow? Is the flow of time a fundamental property of the universe, or merely an artifact of how our brains process information? His theories force us to consider that the strangeness of time might not be in the cosmos, but in the very consciousness that observes it. If Dunne was even partially correct, then the key to understanding quantum gravity, the unification of the large and the small, might require us to fundamentally reconfigure our relationship with time itself. He saw time as a landscape we are only beginning to learn how to read. And if time itself has a hidden, foamy texture at its smallest scales, then the next forgotten genius was the first to predict its bubbling, chaotic nature. John Archibald Wheeler saw the fabric of reality itself as a turbulent, bubbling sea. This towering physicist gave it a name, quantum foam, a chaotic frenzy occurring at the smallest possible scales of existence. Here, at the Planck length, the very concepts of space and time break down. Wheeler envisioned spacetime not as a smooth, continuous stage, but as a seething, foamy ocean where virtual particles and energy fluctuations constantly pop into and out of existence. In this frantic dance, microscopic wormholes might form and evaporate in an instant, and tiny black holes could blink in and out of reality. This was not mere philosophical speculation. Wheeler was mathematically describing the inherent graininess of spacetime, a radical prediction that directly informs modern efforts like loop quantum gravity and string theory, which seek to quantize gravity itself. His grander framework, called geometrodynamics, went even further. He attempted to show that all particles and forces, every electron and every photon, could be understood as nothing more than intricate knots and twists in the curvature of spacetime itself. In this view, the entire cosmos is pure geometry. This breathtaking vision foreshadowed one of the most profound ideas in modern theoretical physics, the holographic principle. Wheeler suggested that the information describing a volume of space could be entirely encoded on its surrounding surface, like a three-dimensional movie being projected from a two-dimensional screen. This led him to his most famous and enigmatic phrase, it from bit. He proposed that every particle, every field of force, even space-time itself, ultimately derives its existence from immaterial bits of information. The physical universe, the it, emerges from the binary yes or no questions posed by quantum interactions, the bits. This was a stunning prediction, one that now lies at the heart of black hole thermodynamics, where information is conserved on the event horizon, and in the very architecture of quantum computers, which process information in fundamentally new ways. Despite his prominence, some of his most profound ideas were met with skepticism. His participatory universe concept suggested that observation is not a passive act, but somehow brings reality into definite existence, a notion that continues to inspire cutting-edge research into the foundations of quantum mechanics. Wheeler's genius was in using powerful metaphors to unveil behaviors we are still struggling to mathematically prove. He looked into the heart of nothingness and saw the blueprint for everything. And as he charted the chaotic microcosm, another mind was meticulously mapping the vast, invisible skeleton of the cosmos on the grandest of scales. Fritz Zwicky peered through his telescope at the Coma cluster, a swirling metropolis of distant galaxies, and saw a problem. The galaxies were racing around the cluster's center at impossible speeds. According to the laws of gravity, the sheer force of their motion should have sent them flying off into the void of intergalactic space. The only thing holding them together should have been the gravitational glue of all the visible matter, the combined mass of billions of stars. But Zwicky's calculations revealed a terrifying discrepancy. There simply was not enough visible mass to keep the cluster from flying apart. It was as if he was watching cars whip around a racetrack at 1,000 miles per hour, held on the track by an invisible barrier. In 1933, he proposed a radical solution, a mysterious substance he called Dunkelmaterei, dark matter. He applied a principle known as the virial theorem, a clever way to compare the kinetic energy of the moving galaxies with the gravitational potential energy binding them. The math was unequivocal. For the cluster to be stable, it had to contain hundreds of times more mass than anyone could see. He was predicting that the overwhelming majority of matter in the universe is completely invisible, neither emitting nor reflecting any light. For this astonishing insight, he was largely ridiculed. The evidence was indirect, resting on complex calculations rather than a direct observation, and many of his colleagues dismissed it as a fanciful invention. Zwicky's own abrasive personality did not help. He was known for his fierce independence and sharp tongue, once referring to his detractors as spherical bastards, because, he said, they were bastards no matter which way you looked at them. This tendency to work in isolation and openly challenge the establishment meant his revolutionary idea was sidelined for decades. Yet, his foresight did not stop there. He also predicted that massive galaxy clusters would act as gravitational lenses, bending the light from even more distant objects behind them, a phenomenon that is now a standard tool for mapping the cosmos. He even correctly theorized that cosmic rays originated from beyond our solar system. Zwicky's story is a stark lesson in how the messenger can sometimes obscure the message, how personal dynamics can delay our acceptance of a profound truth. His persistence in the face of rejection ultimately gave us the bedrock of modern cosmology. Without dark matter, galaxies would never have formed, and the universe would be a vastly different and far emptier place. It forces us to ask, what other invisible realities are we still refusing to see because the evidence challenges our comfortable view of the cosmos? Just as Zwicky mapped the universe's hidden mass, another visionary began to see an intricate, repeating pattern in the apparent chaos of the cosmos. Benoit Mandelbrot saw the jagged edge of a coastline not as a flaw, but as a key to the cosmos. He was a mathematician who championed the beauty of roughness, the hidden order within apparent chaos. While others sought perfect spheres and smooth curves, Mandelbrot developed fractal geometry, a new mathematical language for describing the irregular shapes that nature actually produces. He famously declared that clouds are not spheres, mountains are not cones, and coastlines are not smooth arcs. They are infinitely complex, with patterns that repeat themselves at different scales. Zoom in on a tiny section of a rocky coast, and its jagged outline will look remarkably similar to the entire coastline seen from space. This principle of self-similarity, he boldly proposed, was not just an earthly curiosity, but a fundamental architectural blueprint for the universe itself. He applied this fractal vision to cosmology, suggesting that the distribution of galaxies was not random or uniform, but followed a hierarchical clustering pattern. Galaxies group into clusters, which themselves group into superclusters, forming vast, filamentary walls and immense, empty voids in a cosmic web. This was a direct challenge to the standard cosmological assumption of a smooth, homogeneous universe on the largest scales. For years, his idea was met with deep skepticism, seen as a mathematical abstraction with little bearing on real astrophysics. Then, massive galaxy redshift surveys like the Sloan Digital Sky Survey began to map the cosmos in 3 dimensions. The results were stunning. The universe revealed itself as a sprawling, web-like structure of galaxies, with dense nodes connected by delicate filaments and enormous, dark bubbles of nothingness in between. Exactly the kind of fractal-like pattern Mandelbrot had predicted. His concept of scale invariance now helps physicists analyze the subtle fluctuations in the cosmic microwave background and model the way dark matter halos cluster together, building the universe's visible skeleton. Mandelbrot gave us the tools to see the universe's intricate, repeating signature. A signature written not in straight lines, but in endless, branching complexity. If the grand architecture of the cosmos is truly fractal, then perhaps the path to unifying the largest scales with the smallest quantum realms lies in understanding this universal pattern. His vision of a scale-invariant cosmos introduces our next genius, who foresaw the role of pure chaos in governing the clockwork of the heavens. Henri Poincaré found chaos hidden within Isaac Newton's clockwork universe. While grappling with the notorious 3-body problem, the challenge of predicting how 3 gravitationally bound objects move, he made a startling discovery. The equations were deterministic, meaning they followed strict mathematical rules, but their long-term outcomes were fundamentally unpredictable. A minuscule alteration in the starting positions or velocities of the celestial bodies, a difference no greater than the weight of a single atom, could cascade over time into a completely different cosmic arrangement. One planet might settle into a stable orbit, while another, from an almost identical starting point, could be flung violently into the depths of interstellar space. Poincaré had uncovered the seed of what we now call the butterfly effect. Decades before the term was ever coined, he was essentially proving that perfect prediction in a complex gravitational dance is impossible, not because of flawed equations, but because of the universe's own innate sensitivity. His mathematical genius did not stop there. Through his pioneering work in topology, the study of shapes and spaces, he developed the concept of strange attractors. These are not physical objects, but elegant patterns within chaos itself, toward which a chaotic system inevitably evolves. Imagine a distant solar system with multiple planets, their paths intertwined in a seemingly random ballet. Poincaré showed that their motion, while unpredictable in detail, is confined to a specific, beautiful geometric structure in an abstract mathematical space. This profound insight provided the very foundation for chaos theory, a field that would not formally emerge until the mid-20th century, when computers became powerful enough to simulate the intricate behaviors his equations had already described. For decades, his revelations were a curiosity, a brilliant mind's solitary foray into a realm of physics too complex for his era to fully appreciate. Today, we see Poincaré's fingerprints everywhere. His chaos shapes the formation of galaxies, where tiny density fluctuations in the early universe snowballed into the vast cosmic web we observe. It governs the turbulent weather patterns on alien worlds and the orbital stability of newly discovered exoplanets circling binary stars. Poincaré taught us that the universe is not a perfect, predictable machine, but a vibrant, dynamic system where a whisper of a beginning can roar into a future of infinite variation. His story is a humbling reminder that some of the most profound truths are not found in perfect order, but in the beautiful, mathematical turbulence just beneath the surface. And if the vacuum of space itself is not empty, but seething with this same kind of unpredictable, energetic potential, then our next thinker was the first to hear its faint, quantum hum. Paul Dirac stared into the equations for the electron and saw a mirror world staring back. His own formula, the Dirac equation, was a triumph that perfectly described the electron's behavior and earned him a Nobel Prize. Yet it came with a bizarre and unsettling prediction. The math demanded the existence of a twin for every particle, a perfect copy but with opposite charge. He called it antimatter, and it was confirmed just a few years later with the discovery of the positron. But Dirac's vision went even deeper than a simple particle duo. He realized that his equations painted a picture of the vacuum itself not as a true emptiness, but as a turbulent, seething ocean. This quantum vacuum, he proposed, was a plasma of virtual particle-antiparticle pairs constantly flickering into existence and vanishing almost instantly, borrowing energy from the void before annihilating and paying it back. This was not a philosophical idea. It was a mathematical consequence, a fundamental hum at the heart of reality. This prediction of zero-point energy became the bedrock of quantum field theory, the framework for all modern particle physics. We can even witness its effects. The Casimir effect, where two uncharged metal plates placed infinitesimally close in a vacuum are pushed together by the sheer pressure of these virtual particles popping in and out of existence outside them, is a direct experimental proof that empty space is not empty at all. Dirac took this a step further, speculating that this infinite energy density of the vacuum could be the very source of the cosmological constant, that enigmatic force driving the universe's expansion. Decades later, this exact idea would form the core of our standard model of cosmology, where dark energy is modeled as the energy of the vacuum itself. But Dirac's theoretical courage did not stop there. He was troubled by the immense and seemingly random numbers that defined our universe, like the ratio of the electrical force to the gravitational force between a proton and an electron. He proposed his large number hypothesis, suggesting that these fundamental constants might not be constant at all, but could be slowly changing over the vast lifespan of the cosmos. This radical idea, largely set aside in his time, now fuels active research into theories of varying constants, with astronomers meticulously measuring the light from distant quasars to see if the fine structure constant was different billions of years ago. Even his most speculative work, contemplating the stability of the vacuum and the possibility of its decay, now informs our most dramatic cosmological models, including the idea of a multiverse with different pockets of space, each with their own physical laws. For all his fame, these profound speculations were often overshadowed by his more concrete, proven discoveries. Yet they reveal a mind willing to follow the mathematics into the strangest corners of reality, showing that true genius lies not just in solving known problems, but in using equations to ask questions we never knew we should be asking. His work suggests that the universe is fundamentally computational, a dynamic system processing information at every point. This idea of a cosmos that calculates its own existence leads us directly to the next visionary, who first proposed that reality itself might be the output of a grand cosmic computer. Konrad Zuse constructed the first programmable computer in his parents' living room, a tangle of relays and metal that clicked and whirred into a new age. Decades later, this same engineer peered past his own creation and saw the universe itself. In 1969, he proposed a theory so radical it seemed like science fiction. What if the cosmos is not a continuous, analog reality, but a vast digital computation? Zuse suggested that physical laws are not fundamental. They emerge from a deeper layer of discrete digital processes, as if the universe were running on a cosmic computer. He envisioned spacetime not as a smooth fabric, but as a grid of cellular automata, a lattice of simple cells where each point follows a local set of rules, communicating only with its immediate neighbors. From these minimal, local interactions, the immense complexity of galaxies, life, and consciousness could spontaneously arise, much like the intricate patterns that emerge from the simple rules of Conway's game of life on a computer screen. This was a breathtaking prediction. It directly prefigures modern causal set theory, which posits that spacetime is a collection of discrete events, and loop quantum gravity, which describes space as a network of tiny, quantized loops. Zuse was essentially saying that quantum indeterminacy, that strange fuzziness where particles lack definite states, might not be a flaw in our understanding. It could be a fundamental feature of the system, a consequence of the universe processing information at a finite resolution, like pixels on a screen. His concept that reality is computable aligns perfectly with contemporary efforts to derive physics from information theory. The entropy of a black hole, which we now understand is proportional to the surface area of its event horizon, is essentially a measure of information lost. The entire field of quantum information treats states as bits that can be entangled and processed. For blending computer science with fundamental physics, Zuse was largely dismissed. His ideas were too interdisciplinary, falling into the gap between established fields. Yet, if his digital physics had been taken seriously, we might already have a working computational model of the cosmos, a set of algorithms generating the laws we take as immutable. His story is a powerful testament to how innovation flourishes at the boundaries between disciplines, where few dare to look. This digital perspective of a universe built from information sets the stage for a genius who foresaw how perfect symmetry must shatter to create the rich reality we inhabit. The universe began in a state of perfect symmetry, a featureless and balanced plane of energy. Yoichiro Nambu asked a simple, revolutionary question: what if that perfection had to shatter for our world to exist? He found his answer not by looking at the stars, but by studying the strange behavior of metals chilled to near absolute zero. In superconductors, he saw how a collective dance of electrons could suddenly and spontaneously break a fundamental symmetry, allowing them to flow without resistance. Nambu made a breathtaking conceptual leap, proposing that the entire cosmos underwent a similar phase transition in its first moments. He called this spontaneous symmetry breaking. Just as liquid water, perfectly symmetrical in all directions, suddenly crystallizes into a structured, asymmetrical ice lattice, the newborn universe cooled and fractured from a state of perfect balance into the lopsided reality we know. His specific work on chiral symmetry breaking and the Nambu-Jonah-Lacinio model provided the mathematical proof that this cosmic shattering was not a flaw, but the very mechanism that gives particles their mass. He was describing the Higgs mechanism years before Peter Higgs and others formalized it, predicting an invisible field that permeates all of space, dragging on particles to give them substance. Without this broken symmetry, electrons would whip through the cosmos at the speed of light. Atoms could never form, and stars and planets would be impossible. Nambu's quiet, humble demeanor meant he often worked in the background, his genius overshadowed by more charismatic figures. Yet his insight forms the bedrock of the entire standard model of particle physics. He saw that the same principles governing electrons in a lab superconductor also governed the inflationary expansion of the universe, where a similar symmetry-breaking event caused space itself to expand faster than light, seeding the vast cosmic web of galaxies. His ability to find universal patterns across different scales of reality, from the infinitesimal quantum world to the grand cosmological stage, was a masterclass in intuitive genius. It reveals a profound truth about discovery, that collaborative curiosity and a willingness to connect disparate fields can unlock the universe's deepest operating manual. The cosmos we inhabit is built from the beautiful, necessary fragments of a broken perfection. And if the universe cracked as it cooled, it would have left behind cosmic scars, topological defects in the fabric of spacetime first predicted by our next visionary. Thomas Kibble saw the early universe cooling like a pot of molten metal, its perfect symmetry cracking as it solidified. As a British theoretical physicist in the 1970s, he calculated that these cosmic phase transitions would not be perfectly smooth. Just as ice crystals form along imperfections when water freezes, Kibble predicted that the rapid cooling of the primordial cosmos would have left behind its own scars, which he called topological defects. Among the most fascinating of these are cosmic strings, unimaginably thin, one-dimensional filaments of pure energy thinner than a proton but stretching across billions of light years. Think of them as cracks in the fabric of space-time itself, cosmic fossils from the universe's first moments of existence. Kibble's work on symmetry breaking in gauge theories provided the mathematical foundation for these structures, suggesting they would possess immense density, with a single inch of cosmic string potentially weighing more than a mountain range. Their gravitational influence would be profound, warping the space around them and acting as seeds for the formation of the very first galaxies, pulling matter into the vast cosmic web we observe today. Even more remarkably, these cosmic scars would be dynamic. If a cosmic string were to vibrate, oscillate, or form a loop, Kibble predicted it would ripple space-time itself, emitting faint gravitational waves that we might now be able to detect with our most sensitive instruments, like pulsar timing arrays. His ideas went beyond strings to include other possible defects like domain walls and textures, each a different kind of imperfection in the universe's evolving structure. For decades, these concepts were considered speculative, beautiful mathematical possibilities with no guarantee of physical reality. Yet, Kibble's interdisciplinary bridge between particle physics and cosmology has proven incredibly fruitful. Astronomers now meticulously scan the cosmic microwave background, the oldest light in the universe, looking for the distinctive temperature variations or lensing effects that a passing cosmic string would imprint. While a direct detection remains elusive, the search itself has deepened our understanding of the universe's thermal history and the fundamental forces at play in its infancy. Kibble's legacy is a powerful reminder that the largest structures in the cosmos might be written in the language of the very small, and that the universe's grand architecture could be shaped by the faintest of flaws in its initial design. This profound link between cosmic defects and information leads us directly to a thinker who envisioned our entire reality as a holographic projection from a lower dimensional surface. Gerard T. Hooft saw a black hole not as a cosmic prison, but as a cosmic projector. This Nobel laureate proposed a startling idea in the 1990s. He suggested that all the information describing the contents within any volume of space, every particle and every force, could be perfectly encoded on its two-dimensional boundary. It is the ultimate compression algorithm, a cosmic hologram where a three-dimensional reality is projected from information painted on a distant surface. Think of the experience of a holographic sticker. It displays a three-dimensional image, yet all the data needed to create that illusion is stored on its flat, two-dimensional surface. T. Hooft was saying our universe might operate on the same principle. His work, later formalized with Leonard Susskind into the holographic principle, directly addressed Stephen Hawking's black hole information paradox. The puzzle of whether information swallowed by a black hole is lost forever. T. Hooft's answer was a resounding no. He mathematically argued that the information about every atom that falls in is not destroyed but is smeared and stored on the event horizon, the black hole's point of no return, and is slowly radiated back out as Hawking radiation. This was more than a solution to a single paradox. It was a radical new framework for physics. He predicted that this holographic encoding could be the key to unifying Einstein's general relativity with quantum mechanics, two theories that have stubbornly refused to cooperate. In his vision, the inconsistencies between the smooth geometry of space-time and the frantic chaos of the quantum world might vanish if both are merely different projections of the same underlying information. This profound idea, that reality is fundamentally made of information, now lies at the heart of the ADS CFT, correspondence in string theory. A powerful duality where a gravitational theory in one set of dimensions is perfectly equivalent to a quantum field theory on its lower dimensional boundary. For this breathtaking leap, T. Hooft initially faced deep skepticism. How could our rich, three-dimensional world be an illusion, a shadow play on a distant cosmological wall? Yet, his prediction forces us to reconsider the very nature of dimensionality and locality. If two points that seem far apart in our world are actually adjacent on the universal projector screen, then distance itself may be a derived concept, not a fundamental one. How might this holographic view reshape our understanding of time, if the past and future are also just fixed data on the cosmic film? T. Hooft's visionary thinking, suggesting our reality is a magnificent illusion, paves the way for a genius who anticipated the universe's grand, cyclic nature. Paul Steinhardt did not believe the universe had only one birthday. While most cosmologists traced everything back to a single Big Bang, Steinhardt, working with Neil Dirac, revived a far more ancient idea. He proposed a cyclic cosmos, an eternal rhythm of creation and destruction where our universe is just one note in an endless symphony. In their stunning model, our entire reality exists on a three-dimensional membrane, or brain, floating within a higher dimensional space. The Big Bang was not a mysterious eruption from nothing, but the result of a collision between our brain and a neighboring one. This cosmic collision injects immense energy, resetting and expanding our universe, beginning a new cycle. Each cycle unfolds over trillions of years with dark energy, that mysterious force driving expansion, playing a crucial role. It first accelerates the universe's growth, spreading matter thin, and then somehow decays, allowing the gravitational pull of the brains to draw them together for another collision. This vision foreshadowed research into phantom energy and the possibility of multiple cosmic epochs, each with its own unique physics. A key strength of this model is how it elegantly sidesteps the need for a singularity, a point of infinite density where the laws of physics break down. Instead of a beginning, there is only a perpetual rhythmic transformation. Steinhardt's theory also makes a specific, testable prediction. It suggests that the cosmic microwave background, the universe's first light, should bear the imprint of these endless cycles, potentially showing faint, concentric circular patterns left over from previous cosmic collisions. This bold framework stands as a direct challenge to the dominant inflationary paradigm, which posits a single, rapid expansion after one Big Bang. Steinhardt argued that his cyclic model could solve the same cosmological puzzles, like the horizon problem of why the universe looks so uniform, without requiring the ad hoc assumptions of inflation. His intellectual courage, his willingness to question a deeply entrenched consensus, is a powerful lesson in the importance of diversity of thought in science. It forces us to ask a profound question: is our universe a one-time event, or are we living in an eternal, breathing entity, where every ending is merely a prelude to another beginning? This vision of a cyclical cosmos, governed by the geometry of higher dimensions, leads us to a theorist who saw that gravity itself might have a subtle, twisting component. Ely Cartan saw the universe not just as a bent sheet, but as a fabric that could also twist. While Einstein's general relativity masterfully described gravity as the curvature of spacetime, this quiet French mathematician proposed an additional geometric quality in the early 20th century, a subtle torque he called torsion. Imagine spacetime not as a simple, flexible rubber sheet, but as a complex material that can both warp and corkscrew. Cartan's work with moving frames in differential geometry provided the rigorous language to describe this twisting, suggesting that the very grid of reality possesses an intrinsic spin. His equations laid the foundation for what would become Einstein-Cartan theory, a refined version of general relativity that incorporates the quantum mechanical spin of particles directly into the fabric of gravity. In this richer geometric picture, the infinitesimal angular momentum of every electron and quark contributes to the gravitational field. influencing the dynamics of the cosmos on the very largest scales. For decades, his profound insight was almost completely overlooked, seen as an unnecessary mathematical complication. Mainstream physics was captivated by the elegance of Einstein's curvature and had little use for Cartan's intricate twists. It was not until the late 20th century, when theorists began grappling with the formidable challenge of quantum gravity, that his work was resurrected. Physicists exploring string theory and loop quantum gravity found that torsion fields naturally emerge in their frameworks, potentially offering new explanations for the universe's most stubborn mysteries. Could the diffuse halo of dark matter holding galaxies together be a manifestation of spacetime's twisted geometry on cosmic scales? Might the accelerated expansion of the universe be driven not by a mysterious dark energy, but by the cumulative gravitational effects of universal particle spin described by Cartan's equations? His story is a masterclass in the power of pure mathematics to guide physical intuition, often decades before experimentalists know where to look. The long lag between his abstract discovery and its potential physical application forces a humbling question. How many other answers to our current cosmological puzzles are already hidden in the pages of old mathematical journals, waiting for us to develop the wisdom to understand their language? Cartan's geometric vision of a spinning cosmos seamlessly introduces a genius who predicted the ghostly dance of particles that barely interact with our world at all. Bruno Pontecorvo watched the ghostly trails of particles in his detector and saw a universe in flux. This nuclear physicist made a stunning prediction in the 1950s, suggesting that neutrinos, the most elusive and abundant particles in the cosmos, were not stable identities. He proposed they could oscillate, spontaneously changing from one type to another as they traveled across immense distances through space. His insight was born from a brilliant analogy. He saw similarities between the strange behavior of kaons, other subatomic particles that oscillate between matter and antimatter, and the quantum mechanical nature of neutrinos. Pontecorvo theorized that lepton flavor, a fundamental quantum property, was not a conserved quantity in nature. This was a direct challenge to the emerging standard model of particle physics, which at the time assumed neutrinos were completely massless, an assumption that made such oscillations impossible. For decades, his radical idea was met with deep skepticism. How could a particle with no mass transform itself? The evidence, however, began to mount from an unexpected direction. Experiments designed to detect neutrinos coming from the Sun consistently found a deficit, only measuring about 1/3 of the number predicted by solar models. Pontecorvo's oscillation provided the elegant solution. The electron neutrinos produced in the Sun's core were not disappearing. They were simply changing into muon and tau neutrinos on their journey to Earth, becoming invisible to the detectors of the era. It took until the late 1990s for the super kamiok, an experiment in Japan, to provide definitive, direct confirmation, showing that neutrinos do indeed oscillate and therefore must possess a tiny, but non-zero mass. This discovery was so profound it earned the Nobel Prize in Physics in 2002. Though Pontecorvo had passed away years earlier, his genius never formally recognized by the committee. His foresight did more than solve a solar puzzle. It opened an entirely new window onto the universe. We now understand that neutrino oscillations play a crucial role in the violent mechanics of supernova explosions, helping to blow apart massive stars. They may even hold the key to one of cosmology's greatest mysteries: why the universe is made almost entirely of matter and not antimatter. This process, called leptogenesis, suggests that oscillations in the early universe could have triggered a slight preference for matter, leading to everything we see today. Pontecorvo's story is a powerful testament to theoretical boldness, to following a beautiful analogy into the heart of a cosmic secret. He looked at the faintest whisper of a particle and saw the echo of creation itself. His particle perspective on cosmic transformation leads directly to a genius who anticipated a solitary magnetic pole, a missing piece in the universe's fundamental blueprint. Paul Dirac once again turned his mathematical gaze upon the universe's blueprints and saw a profound imbalance. In 1931, he pointed out that while electricity comes in discrete, individual units, the isolated positive and negative charges of electrons and protons, magnetism stubbornly refuses to do the same. Every magnet we have ever found, from a simple refrigerator magnet to the Earth's own core, is a dipole, always possessing both a north and a south pole. Cut a magnet in half, and you do not get isolated poles. You simply get two smaller magnets, each with its own north and south. This lack of symmetry in Maxwell's equations of electromagnetism bothered Dirac's sense of mathematical beauty. He performed a stunning derivation from quantum mechanics, showing that the mere existence of a single magnetic monopole, an isolated north or south pole, would instantly explain a fundamental mystery: why electric charge itself is quantized, why it only comes in specific, discrete multiples of the electron's charge. He demonstrated that if even one such particle existed somewhere in the cosmos, it would force electric charge to be quantized throughout the entire universe, weaving a thread of perfect symmetry through the laws of physics. This was a breathtaking prediction that a single, unseen particle could dictate a fundamental rule for all of reality. His work ignited a hunt that continues to this day. Physicists have scoured cosmic rays and built elaborate detectors in deep mines, hoping to catch a glimpse of these elusive particles. They have smashed atoms together in powerful particle accelerators like the Large Hadron Collider, attempting to create monopoles in the laboratory, so far without success. Yet, the search has been far from fruitless. Dirac's monopole is not just a missing particle. It is a key that unlocks deeper doors in our theoretical understanding. In grand unified theories which attempt to merge the electromagnetic, weak, and strong nuclear forces, magnetic monopoles are not just possible, they are mandatory. These models suggest that monopoles would have been produced in unimaginable numbers in the searing heat of the universe's first moments. Their puzzling absence today is itself a major clue, one that helped give rise to the theory of cosmic inflation. The idea is that the rapid, exponential expansion of space in the universe's first fraction of a second would have diluted these primordial monopoles, scattering them so far and wide that they became effectively impossible to find. Dirac's mathematical insight also revealed that these monopoles would be topological defects, akin to the cosmic strings predicted by Thomas Kibble, but in a different dimension of the theoretical landscape. They would be stable, massive knots in the fields that permeate reality, permanent relics of a more symmetric epoch. Dirac's legacy here is a masterclass in following the mathematics to its inevitable, beautiful conclusion, showing how the abstract requirement for consistency in our physical laws can dictate the very structure of the cosmos. He saw a hidden connection between the quantum world and the large-scale forces governing the universe, a testament to the power of seeking unity in nature's design. His mind, which gave us antimatter and the quantum vacuum, also gifted us this perfect, symmetrical ghost, a particle that may yet be waiting for us in the vast cosmic dark, holding the reason for one of reality's most basic rules. This profound link between a particle's existence and the universe's fundamental parameters leads us directly to a thinker who explored the ultimate reason why those parameters allow for our own existence. Brandon Carter stood before his colleagues and named a profound cosmic coincidence. He called it the anthropic principle, a simple yet staggering idea that our universe's physical constants are not arbitrary. They appear precisely tuned to allow for our existence. Carter drew a crucial distinction between a weak and a strong version of this principle. The weak anthropic principle is a simple selection effect. It says that we can only observe a universe capable of producing us. In a cosmos with different laws, no one would be around to take notes. The strong version, more controversial, suggests the laws of physics themselves must, in some deep way, allow for the emergence of observers. Carter was predicting the modern puzzle of fine-tuning. Why is the force of gravity exactly as strong as it is? If it were slightly weaker, stars would never have ignited. Slightly stronger, and the universe would have collapsed back on itself in a fiery crunch long before life could form. The cosmological constant, the energy of empty space, is fine-tuned to an even more incredible precision. A change by 1 part in 10 to the power of 120 would have either blown the universe apart too rapidly for galaxies to form or caused it to recollapse instantly. Carter's insight provided a powerful, if unsettling, framework. It forced physicists to ask if our universe is a unique, improbable miracle, or merely one address in a vast multiverse. His principle anticipated the string theory landscape, where countless universes with different physical laws bubble into existence, and eternal inflation, where our observable cosmos is just one pocket in an infinite, self-replicating meta-universe. For this, he was accused of introducing a teleological argument, a backward logic that implied the universe was designed for life. Yet Carter's point was more subtle. He was not arguing for a designer, but for a new kind of scientific reasoning, one that accepts the observer as a fundamental part of the equation. His work compels us to confront our place in the cosmos not as passive witnesses, but as active participants whose very presence reveals the boundaries of physical possibility. If the universe is fine-tuned, was it tuned for us? Or are we simply the lucky outcome of a cosmic lottery with an almost infinite number of losing tickets? This philosophical pivot, from the constants of nature to the role of the observer, leads directly to a genius who saw quantum entanglement as the very engine of cosmic creation. John Stuart Bell worked quietly at CERN, far from the spotlight of academic physics, asking a question others thought was settled. He was deeply troubled by the Copenhagen interpretation's assertion that particles have no definite properties until measured, viewing it as an incomplete description of reality. In 1964, while analyzing the famous Einstein-Podolsky-Rosen paradox, he derived a mathematical proof that would irrevocably change our understanding of the cosmos. His theorem, expressed through the now famous Bell's inequalities, provided a clear, testable criterion. If the world operated on local hidden variables, with no spooky action at a distance, then certain statistical correlations between measured particles would never exceed a specific limit. Quantum mechanics, with its embrace of entanglement, boldly predicted that this limit would be violated. Bell had given physicists a recipe to settle the debate with an experiment, transforming a philosophical argument into a question of hard data. His modest background and position outside the elite university system meant his revolutionary paper was initially met with indifference. It took years for experimentalists like Elaine Aspect to build the delicate apparatus capable of performing the test. When the results came in, they were unequivocal. The quantum correlations broke Bell's inequality, proving that the universe is fundamentally non-local, that two entangled particles can influence each other instantly across any distance, a connection that transcends space and time. Bell had predicted the reality of entanglement long before we had the tools to confirm it, and he foresaw that this profound interconnectedness would have implications far beyond the laboratory. He speculated that non-locality was woven into the fabric of cosmology itself, perhaps playing a role in the quantum origin of the universe, or in the mysterious way information is preserved at the edge of a black hole. Today, his theorem is the bedrock of quantum information science, enabling the secure communication of quantum cryptography and the parallel processing of quantum computers. His story is a powerful testament to how a single independent mind, working with pure logic and persistence, can overturn a foundational dogma and reveal a deeper, stranger layer of cosmic truth. Bell's work forces us to accept that the universe is not a collection of separate objects, but a single, intricately connected whole, where every part somehow knows the state of every other. This profound vision of a participatory, interconnected cosmos finds its ultimate expression in our final genius, who wove all these threads into a single tapestry of cosmic evolution. Julian Barbour erased the arrow of time from the cosmos. This independent physicist proposed a universe without past or future, a static collection of every possible now. He called this timeless landscape Platonia, a realm where every single configuration of the universe, every possible arrangement of every particle, exists eternally. What we perceive as the flow of time, Barbour argued, is merely our consciousness moving through this vast, frozen gallery of moments. Change is not something that happens within time. It is a fundamental, relative difference between one now and another now. This breathtakingly radical idea directly predicts key concepts in modern quantum gravity. His work aligns with the Wheeler-DeWitt equation, which describes a universe without time, and with loop quantum cosmology, where the Big Bang is not a true beginning but a bridge from a previous cosmic phase. Barbour saw the Big Bang itself as just one particular configuration within the endless possibilities of Platonia, a single frame in an infinite cosmic film. His thinking is deeply rooted in Mach's principle, the idea that inertia, the resistance of an object to being moved, is not an intrinsic property but arises from its relationship with all the other matter in the universe. In Barbour's relational mechanics, all motion is relative. An object only moves in relation to other objects, not through some absolute space. This foreshadows the principle of background independence, a cornerstone of both loop quantum gravity and general relativity, which states that spacetime is dynamic, not a fixed stage. It also resonates with the holographic principle, where the description of a volume of space can be encoded on its boundary, another fundamentally relational view of reality. Despite working in solitude, far from the support of major universities, Barbour's timeless physics has steadily influenced contemporary debates. His vision challenges the very heart of our experience. If time is an illusion, then what are we? Our memories are not records of a real past, but simply part of the particular now we inhabit. The urgency we feel, the decay, the progression from cause to effect, all become a kind of cosmic perspective trick. How might this timeless view resolve the epic conflict between quantum theory and gravity? By removing time from the fundamental equation, it sidesteps the problem of reconciling quantum time with the smooth spacetime of relativity. Perhaps the unified theory we seek is not a theory of everything in time, but a theory of the timeless relationships that define the illusion of time. Barbour's holistic perspective is the ultimate encapsulation of our journey. He saw beyond the flow his era took for granted, predicting a universe where every moment is eternal, and every genius, forgotten or remembered, exists in a permanent now, their ideas waiting patiently to be rediscovered. Their collective legacy is a universe far stranger and more wonderful than we ever imagined. A cosmos humming with unseen dimensions, woven from quantum information, and perhaps even timeless at its core. These 27 minds were not mere outliers. They were prophets who listened to a different music, a subtle harmony hidden beneath the noise of accepted dogma. Their stories reveal that discovery is not a straight, triumphant march, but a fragile and often messy dance of intuition, perseverance, and profound isolation. For every celebrated name in our textbooks, there exists a shadow history of brilliant thinkers, whose only crime was being too far ahead of their time. They worked without the support of powerful institutions, their ideas suppressed by societal bias, personal obscurity, or the simple inability of their era to build the tools needed for proof. The straight line of scientific progress is a comforting myth. The reality is a tangled, beautiful web of forgotten connections, where a quiet clergyman predicts black holes with Newton's math, and an aeronautical engineer charts the layered dimensions of time from his dreams. This tapestry of discovery is woven with threads that were once dismissed as nonsense. It forces a humbling reflection. How many of today's fringe theories, currently mocked or ignored, will form the bedrock of tomorrow's physics? The stubborn hunt for magnetic monopoles, the serious consideration of a cyclic universe, the investigation into the nature of consciousness itself. These are the direct descendants of the radical visions we have explored. Each prediction that was later validated, from dark matter's invisible grip to the neutrino's ghostly metamorphosis, began as a whisper against a chorus of consensus. These geniuses teach us the immense value of preserving diverse ideas and challenging established narratives. For the next great leap in understanding often comes from the quiet corner of the lab, the solitary notebook, or the mind willing to ask a question no one else dares to voice. Our current map of the cosmos, from the quantum foam to the cosmic web, is irrevocably shaped by their foresight. They handed us the keys to black holes, illuminated the path to quantum entanglement, and gave us the language to describe the universe's accelerating flight. Let this journey be a reminder to look beyond the mainstream, to listen for the faint signals of genius that history has yet to amplify. Every one of these forgotten voices expands our understanding of reality and deepens our sense of wonder. If this voyage into the minds of those who saw the future of physics has ignited your curiosity, we would love to hear your thoughts. Which of these forgotten geniuses resonated most deeply with you? Share your reflections in the comments below, and subscribe to join us as we continue to uncover the hidden stories and profound mysteries of the universe. Together, we can ensure that no brilliant idea is ever truly lost.